Okay, so in the last class, we just uh, introduced ourselves to the concept of neighbors of a pixel. We understood that there are three different categories of neighbors. One is four neighbors, next is diagonal neighbors, and then eight neighbors. Then we also tried understanding adjacency. Two adjacencies we discussed, four adjacency and eight adjacency. Let us continue this discussion. Just for revision, I will just try to recap what we meant by the different types of neighbors and also the adjacency. Then we will come back and uh, see what is the M adjacency. Okay, so is my OneNote visible?
Yes, sir.
So first, let us just try understanding the four adjacency in simple words. Four neighbors. So as you know, uh, suppose if I just take part of an image, I'll just take a 3 by 3 mask like this. Assume that this is a pixel p of x comma y. Now we saw in the last class that these pixels, okay, these pixels are called the four neighbors. So that's exactly what we have seen in this. Okay, so x plus 1 comma y, x minus 1 comma y, x and y plus 1, x and y minus 1 are the four neighbors. Okay, and so these are the four neighbors, whatever we have shown as tick mark and also in a specific color. Now these these pixels which I am showing now in green color, with respect to p, these pixels, they are called the diagonal neighbors, and they are also four in number actually. Diagonal neighbors, which according to this, it is x plus 1, y plus 1, etc., etc. I think this is a straightforward thing. And a union of these two, that means both of them put together. If I include both these neighbors, then they are called eight neighbors. So this is what we understood in the previous class. Okay, so this is about the neighbors. Now we will talk about the adjacency. Okay, so I'll just take an example and explain this. Let me just consider four adjacency first, and for simplicity, I'll just take uh, maybe I'll just take a binary image. So 0, 1, 0, 1, 1, 1, 0, 1, 1, 0, 1, 0. So I've just taken a binary image just for simplicity, and it can be, in fact, in the last class we discussed for gray shade image. So let us take this as an image. Okay, assume that it is just a 4 cross 4 image. Now I will now the set V can be either 0 or 1. You know that because you have only two gray levels, so I can take the set V as 0 or 1. In this case, I am interested in 1, so I'll just take the set V as 1. Now by definition, let us go back to the definition. 4 adjacency means 2 pixels P and Q should be from the set V. This is very important. That means both of them should be from the set V, and they are said to be adjacent if Q is a 4 neighbor of P. That means it has to satisfy two conditions. It has to satisfy two conditions. Uh, is the screen visible?
Yes, sir.
Okay. So the two conditions it has to satisfy is there is some problem here. Let me just solve that first. What I am writing here, is it visible? This is visible. This part. Okay.
Yes, sir.
Okay. So since the set V is equal to 1, now you can see that these two, let me just show in different color, these two are 4 adjacent. So definitely they are 4 adjacent because they are 4 neighbors and both of them are ones. These two are 4 adjacent. Again these two are 4 adjacent. These two are 4 adjacent. These two are 4 adjacent and these two are 4 adjacent. So the line here is telling that they are adjacent. Okay, adjacency is shown in by just drawing the line. So what I am showing on the picture now, it is for a 4 adjacent image. That means when V is equal to 1, uh, I am just trying to check whether the pixels are adjacent or not. So this is about 4 adjacency. I have just taken an example of uh, only uh, a binary image. I can take an example of, in fact, we have in the last class we took an example. Let me just take that example. So another example, uh, okay, let me just take an example of 10, 12, 14, 15, 18, 10, 12, 11, 10, 11, 12, 13. Some example I'm just taking. And now I am interested in 4 adjacency. What else I should give you?
V.
Yeah, I have to give you V. That means the set V. Let me give the set V as a 10 to 13. Okay, so I'll use red color now to show the adjacency. So it's easy for you. 10 and 12 are 4 connected, are 4 adjacent. These are 4 adjacent, 4 adjacent. 12 and 11 are 4 adjacent. These are 4 adjacent. Okay, I hope it is clear. Any other connections? I think I have covered all of them. So this is one way. They will give you an image, they will give you V and they'll say show all the 4 connected images or 4 adjacent, sorry, all the 4 connected pixels are 4 adjacent pixels. The second way of asking the question is the same question. They will just give you P here and Q somewhere here, say. That means this pixel is P, this pixel is Q. The question will be like this. The question is, are the pixels P and Q 4 adjacent? This is the question. And the question continues, if yes, what is the length of the path? Length of path. This is what they will give you. Okay. Now, can you answer this question now? What are they 4 adjacent? Pixel P and pixel Q.
Yes, sir. They are
Okay.
4 adjacent.
So I can probably show you all the pixels which are connecting it. So this pixel, this, of course, this is one path that I can take. Okay. So the length of the path is one length here, sorry, one unit, one unit, one unit, one unit, and one unit here. So it is 1 plus 1, 2, 3, 4, 5. So the answer for this question is yes, and the length is how much? What is the length?
5.
Yeah, 5. So this is how the questions can be given. So they will ask you what is for adjacency. They will it may be asked to show the adjacency for a given image. The image can be binary, or it can be um, maybe a gray shade image. So this is for a binary image. This is for a gray shade image. Okay. Now let us take another example. Say 8 adjacency. I'll take.
Excuse me, sir.
Yes, please. Yes, yes.
Sir, sir, is it necessary to take the shortest path?
No, no, that
Like,
again,
not
yeah, if they see, if
is-
they ask you the question, length of the shortest path, I think what you said is correct. And usually we take the shortest path. In fact, when they ask the question, they'll usually include this also. I think that's a good point that you raised. If yes, what is the length of the shortest path? So, because as you rightly pointed out, I can go to this Q from P using this path. Correct? No, I can also use this path. So observe here, it is 1, 2, 3, 4, 5, 6, 7. The length of the path is 7 here. Whereas in this case, the length of the path is 5. So shortest path is taken. Okay. Is that okay? Have I cleared your point doubt?
yes, sir.
Okay. Okay. I think there is some issue with my screen. Let me just rectify it and come back. Okay. Yeah. Now let us take 8 connectivity. I think there is a problem. Uh, okay. Give me a minute. I'll just close this and then again come back. Just give me a minute. Okay, I think I still could not solve it, but let us not waste our time. I'll just try to manage today. By next class, I'll adjust it. Let us not waste time. Okay, is my voice clear now?
Yes, sir.
Yes, sir. Your voice is clear.
Hello, am I audible?
Yes, sir. You are audible.
Okay, so okay, I think 50% of the screen I am unable to use, but that's okay. I can manage with this only. I think I have to pull this down, but I am not able to do it. I don't know where is the problem. Even if I do this, it is not coming down. Yeah, let us not waste our time. I'll just try to manage with this screen only for today. I'll set it up by next class. Okay, so let us now try to take 8 connectivity or 8 adjacency. Both of them are same. So maybe I'll just take a different example. just to understand. So this is 12, 15, 16, 18, 20, 12, 13, 11, 12, 14, 15, 18, 1, 12, 13, 12. So if I take this image, now again the question that I would like to ask here is, if I just call this pixel as P and this pixel as Q, the question that I want to ask is, are P and Q 8 adjacent? That is the first question. Your answer should be yes or no for this. If yes, show the shortest path, and find the length of that path. So that would be the next part of the question. If yes, otherwise definitely there won't be any path. So I'll use uh, green color to show. And what else to be given? V. So let me give V as say 12 to 15. Some set I'll give you. So yes, so 12 to 15, these two are connected. These two are connected. 12 to 15, so these two are connected, 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 connected. Okay, this is what I have shown. I am just considering only the 4 neighbors, but you know 8 connectivity means this connection is also there. This connection will also be there. This connection, because they are 8 neighbors. Okay, I hope you can understand. Any other connection? Yeah, I think there is one more connection here. Any other which is missing in this? I think I have, yeah,
No,
any
sir.
other? I have
No,
covered
sir.
all of them. Okay. But what you notice is there are some multiple connections, as you can see. For example, this pixel 14 and 13 have got multiple paths. How to take care of this? We will take the next connectivity. But right now, the question is, are P and Q 8 adjacent? Show the shortest path. So the shortest path would be, uh, I'll just mark this connection, this connection, that means the diagonal connection and diagonal connection. So the length of the shortest path is 3 actually. Okay, that means 1, 2 and 3. So hope the point is clear. This is how we can do 8 connectivity, and you can also find the shortest path. There are multiple paths, but we are taking the shortest path. So let me now go back to our slide. So 8 adjacency we have done. They are from the set V, and they should Q should be a 8 neighbor of P. Okay. Now what is M adjacency? M adjacency is actually again both P and Q should be from set V, and what it says is Q, if it is in the set of N4P, that means your Q should be a 4 neighbor of P. That is one condition. Q can be a diagonal neighbor of P. Q can be a diagonal neighbor of P. But what is important is 4 neighbor of P and 4 neighbor of Q, the intersection of them has to be null. That means there should not be any pixel uh, which is common to 4 neighbor of P and 4 neighbor of Q. Okay, which are from value V. Let us just take a problem and solve this. In fact, I'll just take the same problem. I have to rewrite it. Okay, I'll just rewrite it here only. 12, 15, 16, 18, 20, 12, 13, 11, 12, 14, 15, 18, 1, 12, 13, 12. So we will take the same example just to see that it won't have any ambiguity. Okay, then try to use the condition. Okay, let me just use different color. So maybe I'll use black color. So 12 and 15 here, you know, these are because the set V is same. though there is no difference. Set V is 12 to 15. I think that's what I have given here. Yeah. So 12 and 15 are M connected because 15 is a just see the condition again. Q should be from the set 4 neighbor of P. That means Q should be a 4 neighbor of P. Q can be a diagonal neighbor, but the only condition is 4 neighbor of P and 4 neighbor of Q intersection has to be 0. So let us go back to the problem. Okay. So 12 and 15 are connected. 15 and 12 are connected. Okay. Now, can but okay, these two 12 and 12, they are not connected here. I'm just showing the line, but I'll remove it. They are not connected here. Why do I say they are not connected? You know that 12 is a diagonal neighbor of P. So what you can observe here is this 15 is from the set V. It is common 4 neighbor of this 12 and 4 neighbor of this 12. That means if I call this as P, if I call this as Q, 15 here, 15 is a common 4 neighbor of P and Q. Is my point clear?
Yes, sir.
Because it is in the set. If this were to be say 16, then I could have connected 12 and 12 here in this way. If this were to be 16, but since it is 15, it is from the set V, and it is a common 4. In fact, it is a 4 neighbor of both P and Q. So that is why this connectivity is not there. I hope you have understood it. Okay. Now coming to 12 and 13, they are connected. 13 and 15 are connected. 12 and 14 are connected. 14 and 15 are connected. This 12 and this 15 are not M connected because again the same condition. 14, 13, they are common 4 neighbors of 12 and 15. So they are not connected. So you can observe that the cross connections here, what you were seeing is missing here in this example. Again, this is connected, this is connected. Okay. And this is connected, this is connected, but this cross connection is missing. This connection will not be there because they are it is not satisfying the condition. Okay. Have I made the point clear? So you can observe in this case here there is ambiguity, here, and here you don't have that ambiguity. That means that cross diagonal connections are not there. Okay. So that is actually what is written if you carefully look at the slide. M adjacency eliminates the ambiguities that often arise when 8 adjacency is used. So what you saw here is this was an 8 adjacent pixel. This connection was there in 8 adjacency, but it is missing here because of the condition that we have put in. Okay. I think this is well I explained by one more image. Now carefully observe here. This is a binary image. V is equal to 1, and what you see here, they are 8 adjacent pixels. I think it's not difficult for you to understand. So this are they are connected. These are 8 connected, these are also connected. So you could see that going from this pixel to this pixel, either I can have this path or I can have this path. Okay. So there is an ambiguity. Now if I use M adjacency or M connectivity, I cannot show these two M connected because this is from the set V and it is common for neighbor of this one and this one. That is why this connection is missing here. Okay, so ambiguity is eliminated. I hope I have made it clear. Any doubt?
No, sir.
Okay, so normally there would be question on this. So let me give one question on this. Okay, so I think I have covered all of them. What the question would be like this: usually, an image will be given. You will be given P and Q, and the question will. I'll not make the entries because it's an obvious thing. Are pixels P and Q number one 4 adjacent, number two 8 adjacent, and number three M adjacent. Okay, this is the first question. So your answer for this would be yes or no depending on the connectivity. Next is if yes, find the length of the length of the path. Okay. Now since you have to do all the three, please don't show all the connections using same figure. It would be time consuming, but still I suggest you write one separate figure for 4 adjacency, one separate figure for 8 adjacency, and one separate figure for M adjacency. Okay. Then show the connections according to the and see whether there is a connection or not. If it is there, try to find the shortest path. Okay. So this is how the questions will be there in this topic. Okay. Which to verify whether pixels are adjacent or not. That means whether there is a connectivity or not. So it could be a binary image, it can be a gray shade image. If it is binary image, your V will be either 0 or 1. If it is a gray shade image, your V will be in some range. Okay. Now you may ask me a question, what is the use of this concept? Why should I know the adjacency of pixels? So that will be explained using the next slide. Uh, uh, See what we are seeing here is it's an image. In that image I'm just taking one part of the image and I'm taking another part of the image. So now I may be interested in knowing whether these two parts of the image or these two subsets of an image are adjacent or not in terms of either 4 or 8 or m. Okay. The answer is very simple. If you find at least one pixel which is 4 adjacent to one pixel from this subset, then we say these two are 4 adjacent. So I need only one pixel which connects S2 to S1 with the definition of 4 or 8 or m. So let us just try to see that V is equal to 1 in this case also. You can see that there is a pixel 1 here, but this pixel is 0, so they are not connected. And there is no other way you can connect by using 4 adjacency because this is the only way. So you can observe that S1 and S2 in this case, these two subsets are not 4 connected. I, I hope the point is clear because there is no pixel from the subset S1 which has a 4 connectivity with the pixels with subset S2. That is why they are not 4 connected, but they are 8 connected. Carefully observe this one and this one, they are 8 connected because both of them are from the set V, and also this is an 8 neighbor of this. So I can say S1 and S2 are 8 connected, whereas of course they are also M connected because this is a diagonal neighbor of this, and you can see that there is no uh, pixel which is common, for no neighbor which is common to both this and this. Therefore they are M connected and 8 connected. Okay. So this is one way I can use this connectivity to see whether some part of an image is adjacent or connected to some other part of an image. This is required for you when you are trying to identify objects. Okay, shape of the objects. This is one thing. The next thing is if I show all these connected components and give a label to it, then I can use this concept to identify the shape of that particular region. Not only that, I can also use this concept to find the area of that particular region. What is an example? For example, in a satellite image, let me just go to, okay, assume that I have a satellite image. This is a satellite image. You know, when I say satellite image, what you normally notice is there would be some roads here and there would be some buildings, there would be maybe some vegetation or maybe forest region, there could be rivers. So you can see all these things. You can expect rivers in a satellite image. There could be, in fact, mountains or hill region. Roads can be there. You can have buildings. There could be maybe some probably canal or water tanks. So, so you will see all these regions. Now, suppose you are appointed as an image processing expert, and what I want you to do is in a given satellite image, see what they do is they'll just take an image at some time t1, which can be today, then after maybe some 3 months, t1 plus 3 months, I'll again capture the image. uh, Assume that I am interested in yield of some particular okay, crop, maybe whatever it is, some crop that I am growing. After 3 months, what is the yield? That's what I want to see. Okay, so which means that I need to find out what is the in fact okay, the yield maybe in terms of if it is paddy, say, if it is paddy, say, I am interested maybe in just the green color. Let us assume that I'm interested in green color here. Okay. So what I need to do is from the satellite image that I have captured, this green color, whatever vegetation region that I have, I need to highlight that, and all other regions should be okay, considered as background. So that means from a raw image, from a raw image, I need to convert it into what is known as a labeled image. All of you should have seen the satellite images that are shown, maybe the weather forecast that they show. They'll actually fill some pseudo color and show you so that it is more presentable. So that is actually labeling. So labeled image means I am just recognizing in a given satellite image the river region, maybe the buildings, maybe the mountain region, maybe the water tank, that means water, or it could be the vegetation. Okay, so I'll just find this region. For example, one application I was telling you in the class long back, there was a project where they were actually trying to evaluate the yield of tomato in a field. So here you are looking for red color. So whatever that is looking red, of course, with the shape of tomato is tomato. The rest of the region is not interested to me. Now, when you want to do this, you need to perform an operation called labeling. So that's what we are trying to understand here. Let me just explain. It is just like an algorithm, and I want you to understand this algorithm because I am expecting you to implement this in the lab. It would be nice if it is implemented. Okay, so let us understand the algorithm. So you will be given an image, and you are asked to okay, in fact, um, label this image by using some numbers. Okay, uh, I will explain with an example later. Okay, so let us just try to do it for four connected pixels. Okay, so when I want to look at four connectivity or any connectivity, I should be given v. In this algorithm, I am taking your image to be a binary image, so v is taken to be 1. All pixels which are white are labeled, and definitely all pixels which are black will not have any label. So the procedure is the following: start scanning the image. pixel by pixel from left to right. Okay, so I'll start from one corner, go to the other corner, pixel by pixel. Then once I complete the first row, I'll come down, take the second row and scan it till the end, and I complete the entire image like this. So first scan, second scan, so first row, second row, etc., etc. So this is what you have to do, go from left to right. Then whenever you travel, you will go to a pixel P, and you need to look at, okay, the at every pixel, you need to label it. So you need to look at two pixels. Let me just take an example. Along with that, I'll explain, which will be easy. Okay, so I'll take a binary image, a simple binary image I'll take. So let me just take this binary image: 1 1 1 0 1 1 0 0 1 1 1 1 1 0 1 0 0 1 0 1. Last row is 1 1 0 0 1. I'm just taking a binary image. We'll just take a simple 5 cross 5 image. And of course, V is equal to 1. I'm just trying to look at 4 connectivity or 4 adjacency, and I'm doing labeling. So as I mentioned, the algorithm is you have to start from the left, start moving. Okay, once you complete it, you will come here. Okay. Okay, so now for example, if I am somewhere here, let us assume that I have come here. My scan is here, so that means my current position is this. Okay, so let me call this current pixel as say P. I have, with the meaning of this is I have already completed this row, and I am coming to this position, correct? That is a procedure I am following, which means what? This pixel you have already labeled, this pixel you have already labeled. Okay, according to this algorithm, these two pixels are taken as R and T. Okay, so let me just take this as R and this as T. I hope my point is clear. When I am at P, I have already completed the first row, first element of the second row, and I am here. Okay, so which means you have already labeled R, you have already labeled T. Now I have to label P. Okay, to label this P, I should look at the label that I have given to R, look at the label that I have already given to T. So that's the algorithm. That's what it says. If P denote the pixel at any step in scanning process, R and T are the upper and left hand neighbors of P. That's what I told you. So the upper and the left hand neighbor of P is R and T. Okay. Okay. Then what you do? Suppose if P is 0, move to the next scanning position. So that means if this is 0, since it doesn't belong to this, you don't need to label it. So you move to the next position. That's what it says. I'll explain it with example. If P is 1, then you have to look at R and T. Now you also know that R and T, both of them can be 0. R can be 1, T can be 0. R can be 0, T can be 1, or both of them can be 1. In fact, in this example, both of them are 1. So what should I do? That's what it is telling me. If both are 0, then which means that I have to assign a new label now to P. If one of them is 1, since it is already labeled, assign that label to P. If both are 1 and have the same labels, assign it to P. If both are 1 and have different labels, assign one of the labels to P and make note that the two are equivalent. And after doing this, you have to come for a second pass. I think with example, it would be clear. Okay. Now carefully observe. I will use L1, L2, L3, etc. for labels. Okay. Let me just remove this. Okay, I am at the first pixel here. Since that is the first pixel and it is equal to 1, I have to give a label to it. So I'll call it as L1. Now I'll go to the second pixel here. So The second pixel means now I should look at R and T. In fact, R in this case will be border, therefore R cannot be considered. So T is here, T is 1. Okay, since T is 1 and it is already labeled, that label has to be copied. So the next label is L1. I am assuming that there is no doubt. If there is any doubt, please ask me. Okay, now the next one is 0, so you don't need to label, just leave it as it is. The next one, when I come here, I should look at this position, there is no pixel there. I should look at this, there is a pixel, but you know this is 0, so which means that I have to assign a new label to this. So I'll just call it as L2. First row there is an ambiguity because you don't have some elements. Now when I come here, when I am here at this position, what should I do? I should use these two. You know this is a border pixel, therefore this I have to see. Since it is 1, I have to copy that label to this. So this will be L1. 0, you don't need to worry. I think I have missed one row. Sorry. Sorry for that. One row I have missed. Uh, what was there here? 1 I think. Sorry, there was a 1 here which is missing. So that will also be L1. That will also be L1. Then 0, then L2. Sorry for that. And this one. Now, can somebody tell me what should be the label to this pixel? Since I have already labeled. Hello?
L3,
L3, correct. Who is it?
Rahul.
Yeah, Rahul, L3, correct. Because this is 0, this is 0. So my algorithm says, let me go back to the algorithm. If both are 0, assign a new label. That's what I'm doing. Okay. So if both are 0, assign a new label. Then this pixel. Okay. What is the label? Can somebody respond? Quick. Another 5 minutes maybe. What should be the label to this pixel? Somebody quick. Purnima T, are you there? Purnima, am I audible?
Yes, sir.
Yeah, so
Yes, sir.
yeah, what is the label to see? When I am here, what you have to see is you have to look at these two. Maybe I'll show you the algorithm. So the condition is in this case both are 1. This is also 1, this is also 1. Those are the two pixels that I have already labeled. That means this and this. Since I have already labeled them, if both are 1, what is the condition? If both are 1 and if they have same labels, there is no ambiguity, assign that. But in our case, both are 1 but they have different labels. When that is the case, assign one of this and make note that the two are equivalent. Okay. So you can see that this is L2 and this is L3. Okay. But so that means both the labels are different. So what you do, you just write it as either L2 or L3, but don't forget somewhere you write it down L2 is same as L3. Am I clear?
Yes, sir.
Yes, sir.
Somebody said no. Shivam,
Yes, sir. Yes, sir.
clear no?
Yes, sir.
Okay. Now when I come to this pixel, the only pixel that I have labeled already is this, and that label is L1, so copy that. And when I come to this pixel, I have to look at this and this, but you know that this is 0, only this is 1 and it is labeled, so you copy that label. When I come to this pixel, again these two are already labeled, one of them is 0, therefore I don't have any ambiguity, this is L1, 0. When I come here, only this pixel is labeled, therefore it is L2. When there is a 0, I don't need to worry. When I come here, it is L1. This is 0. This is L2. Now when I come here, this is not labeled, so that means this should be given a new label. L3 is already assigned, so this has to be L4. This has to be L4 because they are neighbors. This is 0, 0, and this should be L2. Is my point clear now? Is this labeling clear? One pass we have completed.
Yes, sir, clear.
Okay. So the next pass is, that's what it says. So let us go back to the algorithm. So we have completed up to this. Do a second pass by considering the equivalent classes. So now I have to look at these type of classes. So the only thing is L2 and L3. So which means what? Wherever you have L3 in the second pass, make it as L2. That's all you have to do. So I will just make this as L2 now. So which means that there is no L3 now because L2 and L3 are same. Okay. So now if I just show it in the terms of maybe 1, 2, 3, just to avoid L1, L2 and all. So this is label 1. These are zeros, of course. This is 0. This is label 2. Label 2. This is label 2. This is 1, 0, 2, 0, 0, 1, 0, 2. This will be L4. I think 3 is not there. For L4, I'll give the label as 3. This is a count of label now. It's a count. Okay. So how many labels are there?
3 levels, sir.
3 labels are there. In 4 connectivity, I'm still at 4 connectivity. So what this means is, you can treat this whatever is 1 as one in fact segment or one region, and this region is a second region, region 2 and region 3. That means your image now has got 3 regions. 3 labels means 3 regions. So what is the use of this? The use of this is when I am trying to, for example, search for vegetation region. All that looks green, if you assign it as one label, so you will know what is the region in the satellite image where you have vegetation. So since I know the area of the pixel and I know what is the count of pixels where it is green, I can just calculate the area of that particular region. Okay, this is how this concept of connectivity could be used to find different regions in an image. Okay, there is a MATLAB command just to verify my answer is correct. Let me just show that MATLAB command and stop today. Please note, of course, in the video that I send, normally you can read it. Just to treat the values as binary, you have to use a term logical. Okay, so I am giving a matrix here, which is the same matrix which I have considered here. 1 1 1 0 1 1 0 0 1 1 1 1 1 0 1. So just observe in my code the matrix that I have given. So 1 1 1 0 1 1 0 0 1 1 and so on and so forth. So I have given the X is my image. Since I have to treat 0 and 1 as logical, that means binary, you have to okay, write it as logical. If you don't do that, 0 and 1 will be taken as some gray values. Now there is a command in MATLAB called BW label, which will actually do this labeling that I have explained, the algorithm that I have explained. BW label, image is X. If I want 4 adjacency, I give 4 here. If I want 8 adjacency, I'll give 8 here. So it will give me the label. It will also give me the number of labels. Let me just run this and show you the result. How many labels I should get? How
3
many?
levels.
Yeah, 3 labels. So just observe. This is the image and look at the labels. The only difference is I called this as 2 and this as 3, but I think in the algorithm he is running like this probably, or labeling like that. That's all the difference. That means all 2's in my result is 3 there, all threes is 2 there. That's all the difference. It's after all a nomenclature, so you the answer is correct. See, these are all ones, and these are threes, and these two are twos. Okay, I have called them as three. Okay, this is one label, this is second label, this is third label, and the number of labels is equal to 3. Okay, is my point clear? Is this concept clear? Because this is an important, again, this could be implemented on MATLAB, and you can actually do it for a satellite image and try to, this would be one of the projects. Now what I want you to do is, please repeat this for 8 connectivity. Now can anybody tell me what could be the change in 8 connectivity in the algorithm? Quick, I think it's already time. So please think of it. In the next class I'll ask you this question. Meanwhile, just for my requirement, please answer your attendance through this. I'll just share the link in the chat window. Complete the attendance and you can leave the class. We will meet next week. And yesterday actually I had asked you some question regarding whether you have completed on-ramp or not. Only 29 of you have responded to that. The others, if you have completed, please respond to it. Only 29 so far have responded. Most of you have sent your, I think I have received about, yeah, around 29 I have received. Okay, the others who have not completed, please complete it, because we have another assignment next week. By that time I want you to complete. So one who completes the attendance can leave the class.